Hi everyone, today I'll talk about Spark and Neo4j, two extremely powerful tools that doesn't integrate quite easily out of the box. That's why we at LARUS, together with Neo4j, developed the connector that makes Spark and Neo4j work together in a smooth and easy way. Today, I'll tell you the story of the connector and we'll see some obstacles we had to overcome before releasing the first version. I'm Davide, data engineer at LARUS, and I'm not really good at introducing myself, so let's just go over it and introduce my company instead. LARUS was founded in 2004 in Venice by our CEO Lorenzo Speranzoni. We also have offices in Pescara and Rome. Our mission is to create platforms to help companies to become insight-driven, getting the best out of their data. We have experts in data science, data visualization, AI, and machine learning, and we mainly work with NoSQL technology, in particular Neo4j. Speaking of which, this is the timeline of the relationship between LARUS and Neo4j. That starts back in 2011 when our CEO, Lorenzo, met Jim Weber, chief data scientist at Neo4j. And they discussed this new technology that helps user extracting insight from data. From then, it escalated really quickly, arriving to 2020 when we became Neo4j Premier Partner. These are other partners of LARUS, Confluent, Couchbase, Fujitsu, and Linkurious. Let's dive into the agenda for today. We'll quickly see what Spark is and how we decided to integrate Neo4j into it. We'll then see some problems we had to face and overcome in order to release the connector. Eventually, I'll show you how to use the connector and we'll have a small demo. What is Spark? It's a distributed processing framework that performs parallel data processing across a cluster of nodes. Supports a SQL query language and has a streaming API. Data are stored in a dataset and data frames that are, from a structural point of view, tables. These tables can be both static or streaming. In this last case, the data are appended to the table when they arrive on the stream. Also, you can work with both types using the same API, which is pretty cool. In addition, Spark is also polyglot and can be used with Scala, Java, Python, and Erlang. You can use Spark to process large dataset that needs to be partitioned to have decent performance, or can be used to build complex pipelines with multiple transformation of data coming from different sources. And last but not least, is great for iterative algorithms such as map and reduce. Our goal was to avoid user to adopt custom and hacky solutions, providing an official connector with a continuous service, both in terms of development and support. We also wanted to leverage Spark Data Source API version 2 in order to be able to use all the Spark powerful features, like multi-language support, streaming API, and graph-driven machine learning. We decided to deprecate the old connector that was just working with Scala and with some limits in Java. We rewrote everything in Scala using Data Source API version 2. And there is the official Neo4j enterprise support provided by LARUS. And a dedicated team always have an eye on the issue tab on GitHub repository. Repository that is public. The project is open source, so feel free to help us anytime. Last but most important, I think, is the documentation website. We really put a lot of effort into it, and we try always our best to keep it updated and clear. The documentation is actually part of our daily backlog. Let's see some of the challenges we had to face before the release. Unfortunately, the data source API version 2 are relatively new and they like to change. So there is very little documentation available. Databricks released some videos of meetups, but nothing that goes deep enough for us. It wasn't easy to find example as well, and the few we managed to see was still too shallow. So we had to find our way through the code base, reading and interpreting the code and the comments. The lack of documentation is probably due to instability of the API. There were breaking changes even between minor releases, and things changed even more between Spark 2.4 and Spark 3.0. But finally, with Spark 3, the API is still marked as evolving, so we are expecting breaking changes in the future. Actually, Apache Spark 3.1 has been recently released, and it doesn't contain breaking changes, but that was the situation we had at the time. Imagine that at the time we had 3 versions of Spark, each one incompatible with the other 2. We couldn't address all the 3 versions in the first release of the connector, so we had to pick one. It wasn't an easy decision at all. We thought that maybe Spark 2.3 was obsolete and would have been deprecated soon, forcing clients to upgrade to a more recent version. On the other hand, Spark 3.0 was relatively new and probably not widely adopted. These assumptions were confirmed by research on the Neo4j client base and by some talks with the Neo4j field engineers. So we decided to start with Spark 2.4. Some months of work later, we launched the first pre-release of the connector on September 30th. And exactly the same day, they opened an issue asking for Spark 3.0 support. So satisfying. What's the situation now? Spark 2.4 is supported. Spark 3.0 and Spark 3.1 are in pre-release and will be soon released. Spark 2.3 is now on hold and probably won't be supported. Speaking of versions, other than Spark, we had to support the correct Scala versions. For example, Spark 3.4 supports Scala 2.11 and Scala 2.12, but Spark 3.0 supports Scala 2.12 and Scala 2.13 and removed the support for Scala 2.11. One thing, we have to also release a jar for each combination of Spark and Scala. So basically, our jars now look like they have a phone number in it. And so one solution to handle all of these versions was to have a branch for each Spark version, but this was obviously too difficult to maintain, especially if the number of Spark versions to support will increase. Our best solution was to leverage Maven modules feature that allows us to share common code between Spark versions all on the same branch and to have separate commands to build jars. That's a great solution that helps us being more quick, especially with bug fixes, since we have to fix the bug on one branch and not on multiple branches. Plus, if there will be breaking changes in the Spark API in the future, we will just need to add another module, saving a lot of code duplication. Going on, another problem was the Spark data structure. Neo4j doesn't rely on tables and doesn't have nothing that can be related to tables. So mapping nodes and relationship into a table wasn't really straightforward. What we did was to map nodes properties into columns. and create two columns for the relationship, one with the source node ID and the other one with the target node ID. It actually gets a bit more complex than this, but this is the core idea. This bidirectional mapping allowed us to read from and write to Neo4j without needing intermediate mapping. Going on, Spark is based around data frames, as we saw, that are tables. Tables have schema, but Neo4j is schemaless. So we had a problem here as well. We had to find a way to generate a schema from a group of nodes and relationships. So first we flatten the Neo4j result. Then we analyze each property, obtaining the type of each property and eventually creating the schema. But what if a property doesn't exist on all the nodes? For example, here we don't have location property on both nodes. We simply set the property to null where it doesn't exist. But again, what if the property have different types across nodes? For example, in this case, age is an integer and a string. In this case, we cast every value of that property to string, no matter the types involved. For example, if your property is a date in one node and the map in another node, it all became a string. A quick note on partitioning, we do it by using skip limit on the generated query, nothing fancy. Just be aware of the deadlock when writing using multiple partitions. Let's take a look at the final result. There are three ways to read from Neo4j. The first one is by label. For whom is not familiar with Spark, let me first explain the code a little bit. Here, you will see some bits of code are missing, but they are just lines regarding the database connection. So I've removed them to be more clear on what's the core features of the connector. Starting from the Spark variable, that is the Spark session, we specify which format we want to read the data, and then set some options to affect the behavior of the connector. Here in this code, we are asking the connector to return us all the nodes with the labels person and admin. What's happening behind the scenes is pretty simple. The connector uses the option to build a Cypher query and executes it on Neo4j and return the results. Here also you can see the multi-language support, and this is how you do the same thing in Scala, Python, and R. Relationship, it's pretty similar. Here we are asking to read all the nodes of type person connected with a relationship of type acted in to node of type movie. Query, we can simply specify a Cypher query inside the option, and that's the most versatile way to read from Neo4j using the connector. As to writing, we have the same three ways: labels, relationship, and query. In this case, we have a data frame with 3 records, each one with 2 rows, ID and name. With this code, we are telling the connector to write each record as a node of type person, musician, and to set the properties ID and name on each node. Relationships, in this case, the data frame has 4 records, each one with 3 columns. This this code tells the connector to write each record as a node musician with a property name, a node instrument with a property name, and to connect them with a play relationship that has an experience property. Moving on, we can also write using a Cypher query as well. The connector makes available a variable named event that contains all the columns of each record in a data frame. In this way, we can be more flexible using those values. Plus, notice that this data frame represents the team that worked on the connector: David Allen, partner solution architect at Neo4j, Andrea Santurbano, CTO in LARUS, and yours truly. Let's see what other cool stuff the connector has. The push-down filter feature allows us to literally push the filters applied to the Spark connector, to the Spark data frame, all the way to Neo4j. In this way, we will pre-filter, Neo4j will pre-filter all the data, allowing Spark to work with a smaller dataset. In this case, if we add this feature, all the nodes of type movie will be returned to Spark, and Spark will have to deal with a larger data frame. Push-down columns works the same way, but in this case, the requested columns are pushed down to Neo4j, returning just the fields that are needed by the user. Both push-down columns and push-down filters can be disabled via specific options. For the database connection and the query execution, we use the official Neo4j driver, and Cypher DSL is also used for the query generation. We don't rely on GraphX or graph frames, but you can still use them without the connector. So the connector is not required. Let's see some common use cases. For example, you can use the connector to integrate different data sources into Neo4j. Spark supports a variety of sources, and all of these can be used to interact with Neo4j easily with the connector. Can also be used to build ATL pipelines, as we said, or can be a good way to leverage Neo4j Spark data science library with data from different sources. And let's go to see a quick demo as well. For the demo, we will be using some notebooks from our repository that will be shared at the end of the talk. Here you can see the code that I was telling you before that was missing from the slides. Those are the connection parameters for the driver. And here is the option that tells the connector to read all the nodes of type movie from the movie graph we have on the database. As you can see, we see the internal Neo4j ID, the labels of the nodes, and all the properties of the nodes. Here, again, the connections, you have to, at the moment, you have to repeat every time the connection parameters. This will be fixed soon because we recently merged a feature that leverages the Spark default configuration. So you can specify some default configuration on Spark, and you don't have to type every time the username and password. Here we see we want to read the relationship of type acted in that connects persons and movies. So we have all the person that acted inside during a movie. Let's see. These two fields are the table representation of the relationship. As we saw in the slide, these are the ID of the source node and ID of the target node. We see also the internals ID of the relationship and the type of the relationship, the labels of the source and target node, and all the properties of the nodes and relationship. Here we simply specify a cipher query inside the option, and we can basically execute any read query we want. And the connector will automatically generate a data frame with the specified fields in the return statement. So let's go see how we can write data to Neo4j. Here we have a data frame that represents the rush band, and we want to write each member of the rush as a person, musician node. So just by running this bit of code, you can see that we have our 3 nodes with their property name. We can also update our existing node using the mode override. Here we want to add the year every member is born. So we specify this option in particular that tells the connector which property to use to match the nodes. Running this, we get our 3 nodes with the born property. We can also write relationships. Here we have a data set with musicians, the instrument they play, and the years of experience they have. We go and specify which type of relationship we are writing, the source node labels, the target node labels. We also want to map the properties. On the left of the semicolon, we have the name of the property inside the data frame, and on the right we have the name of the property on the node. So here is the same, but here is different. So we are saying to the connector, use the instrument column to take the value to write in the name property on the node. These save modes are essentially saying which keyword we want to use when creating these relationships. For the source node, it will use a create statement, and for the target node, it will use a merge statement. So this is just to avoid duplicates. Once we run that, we see that we have our musician nodes that are connected to instrument nodes via the place relationship. We can update our dataset, still writing relationships. Maybe we want to add some instruments that each musician plays. So here we have still years of experience. We have the name of the musician and the new instrument he plays. So we want to specify the node keys because these are, like in the label example, these are used to match the nodes we want to update. So we use the name for updating the musician, and we use the instrument property to update the instrument. And we still use overwrite also for the source node, because we don't want to create other musician we already have in the database. So override will use merge. We create something like merge musician name or this is the query that will be generated with this option. Running this, we see that we have a musician that plays more than one instrument, and we don't have duplicates. Writing with a query, it's pretty straightforward. We just, as we saw in the slide, write the query we want to run. We have the event variable that represent each line of the data frame, and with this code we want just to add an alias on our musicians. So once we run that, we see that we have our musician with their alias. So what's next on the roadmap of the Spark connector? We want to implement the streaming API of Spark. We also want to add our lang test. We recently added the Python test in our pipeline as well. And also we want to fully support Spark 3 because we are missing one feature at the moment, one minor feature, but we want to fully support it. Here are some useful links to the GitHub repository, to the documentation, the notebook I've been using for the demo, and an article on towards data science that talks about the connector. So thank you very much for your attention. Hope you enjoyed it, and feel free to reach me out if you have any questions. Thank you very much.